Thank you. So this is Asterios. Also in CIDR, you will find Kyriakos. So if you want to ask him very deep implementation questions, he will answer them for you. He sits right in the middle of the left row. Good. So we're going to use the typical example that we have for, let's say, cloud services. Think of a shopping cart that you fill it in with items, right? At some point, you basically need to update the stock and you need to make a payment. And the whole thing has to happen atomically, right? And with consistency. Now, let's leave consistency aside and let's talk about a bit about the services. Long story short, if you have a typical, let's say, two-tier application like this one here, you can have your business code in the, let's say, the service part and all of your data management in the database part. So that's how people have been building all of these systems in the past and even nowadays. So they separate the two. Let's not discuss about why they would separate the two. You can see the advantages easily. Important thing here is that you do not only have the communication between the business code and the database, but also communication and messaging among the business logics, basically, of the different services. And this is where things start to become a bit shaky, because all of this communication in some way has to be basically persisted in the database. If not, you never know when somebody has received the message or not. Okay? Now, in traditional, basically in traditional deployments like this one, you will find out that basically 90% of the code is not the business logic, but the error management. So what you see here is an actual Flask program that some master students have developed in my class that basically marks with green all of the parts that you have useless, useful business logic, and the red part is basically failure management, retries, idempotency, atomicity and consistency recovery, parallelization, auto-scaling, all of this mess. And this does not even include the Kubernetes scripts that these people had to write. And this architecturally is almost state of the art at the moment. It's what people actually do in practice. Now, before you get to me with serverless functions, it's not going to cut it. Okay? I don't want to hear it. The point is that you get stateless functions with no function-to-function calls. There is no transactions, and basically the programming model sucks. If you ever try to do this with Amazon Lambdas, good luck to you. Now, we basically asked the questions whether we can hide all of those cloud failures from the programmer completely or not, right? So let us start with something very basic and we'll see how it goes later. So if I would write these services, this one is the user service that holds, let's say, the balance, the money that somebody has. And if they want to buy an item, they have to calculate the price, basically, of an item times the amount, how many items of that one they need. If I have enough money, I will continue, right? And if I don't have enough money, I will put my money back in my account, right? I will basically fail the payment. Now, if you want to execute this, you will see that you will have to do some messaging here. So you will have to get to call the item price, go all the way to the other side, right? Get the price, execute that part, right? And come back. So what have we done here? Is basically, we have an entity, the user, we have another entity that we call the item. We call those stateful entities, right? They have a local, let's say, state. Every entity basically has and holds state, and we guarantee that this state will be persistent forever, and maybe we can do very consistent transactions across the state of those entities. The programming model basically also forces you to have a key that will never change throughout the lifetime of an entity. So if you think about it, if I call the item here, then I need to go all the way to the other side. It may be running on another partition or machine. I will have to come back with the response and continue from where I left off. Now, if a failure happens here, things are weird. Except, if we can break down this function into atomic parts, right? Let's call them atomic, let's call those atomic parts to be, let's say, purely functional, which means they will hold no local state, and anything they need for them to execute will be given as an input. I execute the stateless part, and then I get to the next one. So what would I do in this case? I will basically call item price, and when that one returns, I will simply call the next function that I have marked with yellow here, with the price as an input, plus the local state of this function as the arguments for this function that I will call by item 2. Now, if you do the same thing, right, you will end up with a bunch of other functions. And what we managed to do here is split a normal imperative program into a series of fully functional functions that each of them can execute one after the other, right? And if anything happens in between this atomic function, you simply rerun it again with the same arguments. Now, where am I going with this one? Basically, if you take all those functions, you can see that you can design something like a data flow graph, right? So from the by item that we have defined here, we go to by item 1, basically this one. Then I will have to go away to execute price of the other thing. Then I will come back to by item 2, and by item 2 will receive the return value of this function and also the local function state that they had up to here. And if you take that data flow graph and you basically do some manipulations, you can generate a very nice streaming data flow graph in which the state of the entity is going to be the state of the operator. Every function call becomes basically an endpoint in that data flow operator. And magically, this thing can be transformed into a concrete program that can execute in any streaming data flow execution engine. In this case, you can run on Flink, on Kafka, on Samza, on anything that can basically execute a data flow graph for you. What do you gain by that? The most important thing is exactly one's processing guarantees, which means that no matter what happens here, no matter what failures will take place, you will simply be able to re-execute the whole thing, and the effects on the state are going to be reflected exactly 1 time. Which means that if you go back to the programming model, we can execute both of those without having one error management line of code. Okay? Now, this thing works. And it can run in parallel. We have a very nice prototype at Delft, and we managed to execute some YCSB workloads. You can get basically extremely low latency in the tens of milliseconds for such function executions. And this part basically, Stateful is, we compiled all those to Apache Flink's Stateful endpoint, and Stateflow is a local, let's say, homemade execution engine that Kyriakos is building right now. And we have managed to get those numbers much, much lower than what you see here. So, to make a long story short, what I wanted to tell you today is that it is possible to take normal, imperative, object-oriented programs, analyze them in some way, create a data flow graph out of those, and then after you create the data flow graph, you can hand it over to any streaming execution engine that will execute it for you with exactly what guarantees, and none of the failures will make it to the programming level. So as long as you have a good operations team to keep Flink alive, it's going to be okay. That's it.